All right. Good afternoon, everyone. My name is Manesh Patel, and we will be getting started with the third module in our series in just a minute. As a reminder, to better get to your questions, please type them into the chat, and the staff will get to them as soon as they can. Do not forget, you can also email questions as well. And if we do run out of time to answer questions verbally after each presentation, we'll try and get to them at the end of the module. So today we'll be tying into what was presented in the two prior modules and apply that information to reviewing projects. So we have how to review a project one, which will be presented by Rachel Werner along with myself. And we have how to review a project two, which will be presented by Lisa Schaefer. After the how to review a project presentations, Peter Pliantos will continue on with groundwater mounding, along with examples of performing the analysis that is required. And then after that, we will have our quiz number 3. So let's get started. I, along with Rachel, who will take over in the second half of this presentation, are going to be going through part 1 of how to review a project. So this presentation came about because our review of approved projects during compliance audits showed that projects were being approved even though the calculations and stormwater management reports that were submitted for local approvals did not comply with the stormwater management rules and the local stormwater control ordinances. Therefore, should these projects fail, the municipalities involved would be in violation of their respective permits. So here are the goals of this presentation, which are by no coincidence the goals of a successful project review. We want reviewers to be able to identify the design and performance standards that must be met on site, review applications for compliance with green infrastructure, stormwater quantity, stormwater quality, groundwater recharge standards, and review BMPs for compliance with the design criteria in the BMP manual. The information required in the stormwater report is specified in the stormwater control ordinance, and checklists are available to help with the review. The reviewer must make sure that any information found missing from the report must be added before approval of the project. The checklist found at this link in the Tier A guidance document can help with your review of the report and help to just organize your observations and comments. Now we're going to look at what the reviewer needs to be looking for in the stormwater management report. So the first step in the project review is to check if the application package is complete. All the items listed here must be part of the application. So pre and post site plans and pre and post grading plans are essential, as are the associated calculations and any drainage area maps. The details in the report sections, they should match up with the information on all plan pages. Too often, we do find that some parts or even all of the stormwater report do not match the site and grading plans because the report was copied from another project. So the reviewer must also be aware of whether or not the permittee has a more stringent standard of what must be in an application for approval. If so, the reviewer should be looking at all that information. The township's adopted ordinance, which should be posted online, is also a great starting place to find what information is required to be submitted. Another issue we see that should be checked right away is that the plans and reports should also be reflected in the maintenance plan so that the BMPs will continue to function as they were designed. Too often we do see maintenance plans submitted that were copied from other projects and do not match at all the project that was submitted. So like I just said, it is important that the reviewer checks that the site description matches up with the plans. The drainage and discharge points all need to be checked along with any change in pervious or impervious coverage that includes regulated impervious surface and regulated motor vehicle surface for each subdrainage area. And then also soil information for the site should be included and be accurate. Lisa covered the use of the web soil survey as a means for getting your soil information, and more guidance will be provided later on today. As a side note, print versions of county soil surveys are not always up to date, and they shouldn't really be used as your sole resource. The report must include the following information regarding design and performance standards when it comes to what's required, along with any applicable variances, waivers, or exemptions, and how the standards will be met. Again, we find that this is often missing or does not match up to what is on the plan, so this is very important that this information is provided. The reviewer must be sure that the following calculations are included in the report. Time of concentration, as was discussed in Module 2 last Thursday by Rachel, is essential to characterizing a site. Time of concentration must be calculated and included in the report. Some permittees may even require this information be submitted on a CD so that it can be checked. But no matter the format, though, it's important to include all of this information, including stormwater routings, hydrographs, the groundwater recharge spreadsheet, the mounting analysis if it's applicable, and water quality calculations, and make sure it actually matches what's on the plans. So you saw this slide earlier in Module 1 last week in the overview presentation. Always check whether the project meets the definition of major development because there could be a chance that it doesn't. Also be sure the permittee's definition of major development in their ordinance as it may be stricter than the department standard. One note here though, you do need to distinguish the different types of surfaces, whether it be regulated motor vehicle surface, regulated impervious surface, other pervious surfaces, and etc. in the report. There are one or more major development thresholds that may apply to the project that the reviewers should be aware of, including the residential site improvement standards, the permittee's stormwater control ordinance, and the NJDEP land use regulations. As you can see here on the slide, each has a definition that you need to pay attention to when you are completing a review. Once the reviewer has verified that the required information has been submitted and is accurate, they can begin to actually review the design and performance standards. The plans and report must address the information that's listed here. This information is crucial to determining whether the project was designed properly. Information such as whether the project is discharging to a flood hazard area or a Category 1 waterway are often not included, and therefore they're overlooked during the review. This information may also determine whether or not the project requires input from other agencies such as the NJDEP Land Use Crew or even the Pinelands Commission. Under the current rules, a reviewer must ensure the proposed design complies with the design criteria that's established in the BMP manual, which in turn ensures the design meets the design and performance standards of the rules. If something is an alternative design or method of calculation, the department must be notified of that approval. Along with the other standards, the reviewers must ensure the BMPs follow the green infrastructure standards. And for this, the BMP manual provides the design criteria and considerations for the individual types of green infrastructure BMPs. If the reviewer did allow for waivers or variances, they must be sure that they were applicable. Can waivers or variances even be granted? It's really not a straightforward answer, and to resolve this somewhat gray area, it's been better defined. So the amendments to 7:8-4.6 were made to clarify the conditions that would warrant the granting of a variance by a municipality for a major development project. The amendments are intended to ensure that municipalities are not granting variances under inappropriate circumstances. Municipalities do not have to grant variances, and they do not have to create a mitigation plan if they don't plan to grant a variance. But if they do, they can create a mitigation plan that allows the evaluation of mitigation projects suggested by applicants, allowing for the consideration of projects that are submitted by applicants as is permitted at NJAC 7:8-4.6. So to eliminate any potential misconception that a variance is an exemption from attaining the stormwater management standards, the word exemption was removed from this section as part of the rule amendment. With the amended version of the rules, the ability to grant variances requires a little more effort by the applicant. Now, there must be a demonstration that it is technically impracticable to meet one or more of the design standards. The only allowable variances are for engineering, environmental, or safety reasons, and they have to be spelled out very, very clearly. Cost is not really a factor here. And the old low impact development checklist often included statements that something was not economically feasible, and yet cost information was not formally reviewed. Previously, there may have been a site-wide variance allowed, but now the rule located at section 4.6 states, a municipality's approval of a variance shall apply to an individual drainage area and design and performance standard and shall not apply to an entire site or project unless an applicant provides the required analysis for each drainage area within the site and each design and performance standard. There's a lot more to the mitigation requirements that must be met to obtain approval of a variance. Mitigation must be part of the municipal stormwater management plan and follow these new requirements. It must be selected from the municipal list of mitigation projects, or it could be proposed by the applicant if it meets the criteria for the municipal mitigation plan. It must be approved no later than the preliminary or final site plan approval. It must be located in the same HUC 14. It must be constructed concurrently or prior to the major development. It must meet the green infrastructure standards. And the entity assuming the responsibility of maintenance for the project must submit a written agreement to the review agency. Lastly, the approved variance must now be submitted to the county review agency and the DEP within 30 days of approval. Mitigation is required to receive a variance from the green infrastructure standards, but be aware that certain BMPs cannot be used as mitigation measures and that there are minimum sizing and drainage area limitations. Note that vegetative filter strips and grass swales are excluded as mitigation measures, and they don't address quantity control and groundwater recharge. Green infrastructure BMPs that are used for mitigation, they do need to be sized to manage the water quality design storm at a minimum, and they are subject to the specified drainage area limitations. Variances from the other standards are as shown on this slide. Note that there is no waiver or variance allowed for groundwater mounding. That's because the steps listed in Chapter 13 of the BMP manual make it clear that if the selected BMP fails to pass the groundwater mounding analysis, another BMP must be selected and assessed, meaning that a whole new redesign is required. The reviewer should also be able to determine whether linear development exemptions exist on the site. The following linear development exemptions may be granted if the requirements are met for each. So that is construction of an underground utility line if revegetated upon completion, construction of an above ground utility line if existing conditions are maintained to the maximum extent practicable, and construction of a public pedestrian access if made of permeable materials and it is no greater than 14 feet wide. Finally, the reviewer may allow waivers to be granted for the enlargement of a road or railroad or the construction or enlargement of a public pedestrian access if the requirements here are met and they are public need for a project that can't be met another way. Design and performance standards met to the maximum extent practicable. Meeting these standards would require condemning existing in-use structures, and the applicant does not have and cannot get rights to other lands for mitigation. These specific exemptions were discussed earlier in Module 1 last week. Water quantity is exempt if it's in a tidal flood hazard area and flooding will not increase. Water quality is exempt if the site has a NGIPD's permit with a specific effluent limit. And groundwater recharge is exempt for previously developed areas in an urban redevelopment area. It is important that the reviewer is aware of what urban redevelopment exemptions are and where they can be applied. Urban redevelopment exemptions can only be granted to previously developed areas of a site. The existence of woody vegetation is a telltale sign of whether this exemption can be granted. So if the reviewer finds that woody vegetation has returned to areas of a previously developed site, the exemption is not going to be allowed. The reason being is that removing woody vegetation and putting new construction over this portion of the site is going to result in a loss of groundwater recharge. And then the reviewer can check the NJ GeoWeb to determine whether the rest of this information is applicable to the site. So in summary, the following are the possible variances, exemptions, and waivers that may be applicable to the site, but it's important that the reviewer takes the time to make sure that they can be applied and that they are only applied to the specific portions of the site that meet these specific requirements. All right, so moving on, the next thing the reviewer should be looking at is if the applicant is meeting the design and performance standards using green infrastructure. The rules do require that the design and performance standards are to be met using green infrastructure. And you can see right here, subsection 5.2 of the rules includes 3 tables, and they list those BMPs that may be used to meet the design and performance standards. The tables found there specify information on how each BMP may be used. So table 5-1 coincides with chapter 9 of the BMP manual, as you can see on your slide right here. And these are the GI BMPs. So they are cisterns, dry wells, grass swales, green roofs, green infrastructure MTDs, pervious paving systems, small scale bioretention systems, small scale filtration basins, small scale GI sand filters, and vegetative filter strips. Some of the BMPs, they cannot receive runoff from motor vehicle surfaces, and therefore they do not address water quality, such as cisterns and green roofs. Others don't offset the discharge of stormwater runoff from the 210 and 100-year design storm, so they cannot meet the quantity control requirement, such as a dry well. And a note here, not all MTDs are considered green infrastructure, but the ones that are considered are included here in Chapter 9. These MTDs have a vegetative or soil component that meet the GI definition. And lastly, these small-scale systems listed here have a limited drainage area that they can treat compared to other BMPs. As you can see, the column on the left includes the name of the BMP, and the column on the right includes the maximum contributory drainage area. So, for example, if you are using a dry well, the maximum contributory drainage area is going to be an acre, MTDs 2.5 acres, and so on. No, we are only talking about MTDs that are approved for GI here. In the past, we have seen projects that propose to design 2 small-scale GI BMPs that each have drainage areas just less than the maximum allowed contributory drainage area that are side by side in the corner of the site so as to try and get around this drainage limitation. However, a design like this is not going to meet the GI definition because GI means a stormwater management measure that manages stormwater close to its source. The design of small-scale GI BMPs shall be distributed throughout the site and manage the runoff closer to the source that it is generating that runoff. So as you can see from the first diagram, there are a bunch of GI BMPs that are clustered together. The second diagram shows 2 large-scale BMPs in proximity of each other. These BMPs would need to be spread out from each other to cover the entirety of the runoff of the site to meet the GI definition. Chapter 10 BMPs can be used to address stormwater runoff quantity control. These BMPs can have larger contributory drainage areas than the BMPs that were listed in Chapter 9. These Chapter 10 BMPs include large-scale bioretention systems, large-scale infiltration basins, large-scale GI sand filters, standard constructed wetlands, and GI wet ponds. Note that though I said they can address quantity, these BMPs may only be used to meet water quality and recharge if a waiver or a variance is granted. BMPs in Chapter 11 are non-green infrastructure, and they're always going to require a waiver or a variance before they can be used. It's not really anticipated that these BMPs will be used much in the future because of what is required in order to grant a waiver or approve a variance. But as for some of the BMPs that are noted on this table, blue roofs don't have a reuse component, and extended detention basins are typically large, and they require additional treatment to meet water quality standards. The majority of MTDs currently do not have a soil or vegetative component, so most of them will fall under this table. And then you see non-GI sand filters, subsurface gravel wetlands, and non-GI wet ponds to round out the rest of Chapter 11. So the next thing the reviewer needs to look at is stormwater runoff quantity control. Or excuse me, water quantity. Water quantity impacts must be addressed to not only prevent increased flooding due to development, but also to avoid increased flow rates, which can significantly degrade water bodies downstream from a site. In Module 1, we did cover the different options a designer can choose to follow. I'll briefly go through the options to meet water quantity control, as we found this is being done incorrectly in many of our reviews. It is important to note that the reviewer must make sure that all points of discharge from the site must meet the water quantity control standard, and if not, then the project is not going to be compliant. So let's begin with taking a look at topography. Topography is very important in identifying where the stormwater flows, and it's required to determine drainage areas and the time of concentration. Reviewers should be able to find the topography information on the plans and make sure that it's accurate. This, in some cases, may even require the reviewer to physically see the site as well. It's often difficult for us to find drainage maps in these stormwater reports. We also see situations where the drainage calculations in the reports do not match up with the drainage maps in the plans. We need to see existing and proposed contours. We need to see the point of analysis, time of concentration flow paths, and the drainage area to each point of analysis. The reviewer must be sure that the data used in the calculations matches the various maps and plans. This information must also be included on the drainage plans. It's very important to understand that each drainage area needs to be calculated separately. The reviewer should see the following calculated separately for each drainage area and must check the calculations for each drainage area. You should not assume that if one calculation is correct, then the rest are correct as well. So here's an example site we have here. The flow was evaluated as sheet flow, directed primarily in a southerly direction. However, we received complaints of flooding along the road that's lying to the east of the project and from the area northwest of the project. So it was determined that the drainage areas were not delineated correctly. Whether or not that was due to an incorrect evaluation of the topography, that's unknown. But this does show why it's important to properly evaluate the topography and delineate the drainage areas. To prevent those issues from occurring, the reviewer must verify that all drainage areas are outlined correctly, the proper time of concentration flow path is used, and time of concentration is calculated properly. The reviewer needs to make sure that any natural ponding on site is included in the model. This is often overlooked, and ignoring it for the existing condition means the allowed proposed volumes will be larger than they actually should be. On that same example site that was shown a couple slides ago, there was a 6-inch deep ponded area within the shape that's depicted here. This was ignored, and the basin was made significantly larger than was needed. If there are any questions as to whether areas of ponding exist on site and it cannot be determined from the photos of the site, you may have to just go there in person and see the actual site for yourself. The reviewer should be checking land cover next. Land cover should be clearly marked on the plans and be specific to what the land actually is. It should also include any existing BMPs on site. The reviewer must verify that the plans and cover descriptions in the report match what is actually on the site. Aerial photos can be used to make sure the most pervious cover that existed in the past 5 years has been used in the calculations. Again, it may be necessary for the reviewer to verify land cover conditions in person to make sure that they have been accurately described. Lisa has gone through how to determine soils, but just to reiterate, it is important to make an accurate determination of the soil types on site. The type of soil will greatly affect the functionality of the BMP. So again, the reviewer can find soil info at the NRCS Web Soil Survey webpage. That's at the link provided here. If information on the site soils cannot be found, you can use the methods that are found in Chapter 12 of the BMP manual to determine hydrologic soil groups, either from the default HFG method or from soil testing itself. Making sure that the soil data for the site is accurate is a critical part of the review process. Inaccurate soil information can make or break a stormwater BMP. So generally, a good practice is to review soil testing first. The rainfall depth and intensity information should come from these sources. You will need to make sure the current precipitation adjustment and future precipitation change factors are appropriately applied for the 2-year, 10-year, and 100-year storm events using these tables on the slide, which are also found in Chapter 5 of the BMP manual. NRCS has developed distributions for New Jersey, including NOAA C and D, which the BMP manual requires use of. These are already built into many stormwater modeling programs such as HydroCAD. So the reviewer should check that the correct distribution is selected, which is also dependent upon where the site is located. The reviewer should next look at time of concentration. Information on how to calculate it can again be found in Chapter 5 of the BMP manual and the National Engineering Handbook. We also need to determine if the time of concentration in the pre-construction is appropriately calculated. We need to make sure that they are not underestimating this value. So we need to make sure that the Manning sheet flow roughness coefficient is 0.4 or less for the TC calculations. According to the NRCS, the maximum Manning's roughness coefficient to be used is 0.8 for woods with dense underbrush, but in New Jersey, we do not have that situation. And the maximum Manning's coefficient for sheet flow in New Jersey that may be used is actually 0.4. Rachel did cover this in Module 2, and you can find more info about this in Chapter 5 of the BMP manual. And as a reminder again, you will need to use the current precipitation adjustment factor and future precipitation change factor tables that are found in Chapter 5 to calculate the travel times for current and projected storm events using the 2-year 24-hour storm event, which will be used to calculate the P2 parameter. So you can look back through the handouts for the calculations presentation from Module 2 for more information on the correct way to calculate time of concentration. So in summary, the reviewer must make sure that the sheet flow, shallow concentrated flow, and channel flow inputs are all correct. They must make sure that the proper time of concentration was used with the corresponding method. They must check the pre-construction time of concentration calculations, and the reviewer must check the post-construction time of concentration calculations. That is, it is no longer allowable to be assumed. Curve numbers are associated with the NRCS methodology and are used to calculate the amount of runoff caused by a specific amount of precipitation. The reviewer must be sure that the curve numbers correspond with each specific area based on land cover and hydrologic soil groups. The curve numbers are based on a presumption of good hydrologic condition, unless the design engineer provides evidence showing different conditions. Again, this was also covered in Module 2. So here's an example of what a land cover table might look like from an engineering report. You can see here the land cover, the area of the cover, soil types, HSGs, and associated curve numbers. The reviewer must check these numbers and land cover types against what is shown on the plans. Sometimes you could see that they do not match up. So always be sure to check and make sure that they correspond to each other. So in all, the reviewer must check that curve numbers are justified in the report. You can verify these in the National Engineering Handbook. And then the reviewer is responsible for making sure the chosen values are reasonable and that they're accurate. Now I'm going to hand it off to Rachel, who will take you through the rest of stormwater runoff quantity.
Thank you, Manesh, and hi, everyone. All right, so now we'll continue with how to review a project for stormwater quantity, quality, and groundwater recharge control. So I just want to point out that most of these requirements, like the unit hydrograph, were already discussed in modules 1 and 2, but now we're going to dive into how to apply these requirements when you review a project, building on modules 1 and 2. So as we discussed before, there are two hydrographs for New Jersey, the SES and the Delmarva. Typically, the SES unit hydrograph is used outside of the coastal plain region, and the Delmarva is used inside the coastal plain region. However, this does not apply if coastal plain conditions do not actually exist, nor for sizing MTDs. So, as a reviewer, you need to make sure that the designer used the correct unit hydrograph. You also need to make sure that they use the same one in the pre and post-construction conditions. The next thing you'll want to check is the runoff routing. So, like we talked about before, the pervious and impervious areas need to be routed separately. A weighted CN cannot be used because it greatly underestimates the total volume of stormwater runoff. So when reviewing the hydrograph printouts, you need to make sure that a weighted CN was not used. In addition to that, because there are multiple subdrainage areas, like pervious and impervious, being routed to a single point of analysis, these subdrainage areas need to be combined to determine the total peak flow rate at the point of analysis. Now, and this is important, you cannot simply arithmetically add the peak flow rates of all the subdrainage areas to get the combined peak flow rate. And do you know why? Because of timing, because of the time of concentration, because the peak flow rate happens at different times for each subdrainage area. So in the hydrology software, all subdrainage areas need to be routed to the appropriate point of analysis for a single combined hydrograph. Moving on to something Manesh briefly touched on at the beginning of this presentation, if there are existing depressions on a site, meaning a place where water will pond before overflowing, they need to be modeled as existing basins. So as a reviewer, if you identify any depression storage areas on a site, you need to make sure that they're included in the model. Not including them can affect the existing time of concentration and ultimately the peak flow rate. These depressions and high permeability soils provide stormwater management benefits that need to be considered. In general, this is the procedure that should be followed to model existing depression storage areas in the middle of a site. And bear with me because we will go through an example for this. So first, model the depression area as a basin, meaning there will be subdrainage areas going to the depression, and the depression will be modeled as a pond using the existing site characteristics. Next, calculate the time of concentration from the depression outlet to the point of analysis. This time of concentration will be used as the lag time between the depression and the point of analysis. Now, what does that mean? That means the depression produces a hydrograph, right, like any basin does. However, the stormwater still has some distance to travel before actually getting to the point of analysis, and we have to account for that. So in HydroCAD, for example, you can place a link between the depression and the point of analysis. And in this link, you can add a lag time. That lag time will be the time of concentration that you calculated from the depression outlet to the point of analysis, basically shifting the time of the hydrograph to the right to account for the travel time. And lastly, you will need to route the other subdrainage areas that do not go through the depression directly to the point of analysis. And a combined hydrograph with the correct timing and peak flow will be the result. Now, this is the same example as before. There was an existing depression storage area between these two contours that both the designer and the reviewer missed. Now, as the reviewer, a good indication that an area needs further examination is two contours of the same elevation next to each other. Because the question becomes, what's happening between the two 50 contours like we have on this plan here? Is it totally flat? Is there a random high point? Or like in this case, is there a random low point where ponding can occur? A site visit during a rain event is also helpful to determine if there are any depression storage areas. All right, so this slide is just digging into the model depression area step from before. To model the depression area, you will need to do what you do for every basin. Determine the time of concentration, calculate the stage storage data for the depression, which is basically the storage volume of the depression, model the outlet from the depression area, which we will go over on the next couple slides, and route the contributory drainage area to the depression area. Taking a closer look at what this would look like in HydroCAD, you have your contributory drainage area, which is the green hexagon, aka a subcatchment, and your depression, which is the blue triangle, aka a pond. The subcatchment will have the drainage area, CN, and time of concentration going to the pond, and the pond will have the depression characteristics to include the volume and any outlets. And taking a look at the HydroCAD summary, this depression was said to range from 49.10 feet to 49.70 feet, with a total volume of 1,228 cubic feet. And the outlet was modeled as a 22-foot long broad-crested weir, which means that stormwater is basically spilling over the side of the depression at elevation of 49.60. And again, all of these inputs are based on existing site characteristics. Okay, now after reviewing all of the input parameters that Manesh and I just went over, the next thing to review is the output to see if it complies with any of the quality control options. And these options were discussed in depth during Module 1. So the first option is to demonstrate that at no point does the post-construction runoff hydrograph exceed the pre-construction hydrograph for the current and projected 210 and 100-year storms. It's important to note that there are four main variables that affect the hydrograph: the drainage area, the curve number, the time of concentration, and the rainfall depth and distribution. So if any of these variables change, it will change the hydrograph. Typically, the drainage area and rainfall depth and distribution will remain the same from pre to post construction conditions, meaning the CN and the TC are the biggest drivers when it comes to meeting this option. The CN value affects the peak flow rate and the volume of runoff. The higher the CN, the higher the peak flow rate and the larger the volume. The TC, the time of concentration, also affects the peak flow rate, the time of the peak flow rate, and the steepness of the hydrograph. The lower the time of concentration, the higher the peak flow rate, the earlier the time of peak flow rate, and the steeper the hydrograph. So generally speaking, the CN value affects the y-axis of the hydrograph, shifting things up and down, and the TC affects the x and y-axis, shifting things up and down and left and right. So even if the CN is decreasing, i.e. the impervious cover is reduced, if the TC, the time of concentration, changes, that could cause the post-construction hydrograph to exceed the pre-construction hydrograph. Now, here's an example directly from Chapter 5 of the B&P manual to demonstrate this option. So for a site located in Trenton, Mercer County, an approximately 2-acre paved parking lot is to be redeveloped as an office complex consisting of a new building, a parking lot, and landscaping. The existing lot has a slope of 1%. The redeveloped site will be regraded to a 5% slope for better drainage. The landscaped area will not receive runoff from the impervious surfaces. HSGC soils are present. So, in this example, we see a proposed redevelopment reducing the overall impervious area, but simultaneously increasing the slope of the impervious area to remain. So what do we think the outcome will be? Well, a summary of the results from the modeling software is shown in the table on the right side of the slide. Please note, to correctly calculate the time of concentration, first, P2 was calculated by multiplying the NOAA rainfall depth for the 2-year storm, which is 3.33 inches, by the future adjustment factor, which is 1.16, and that gives us a P2 of 3.86 inches. So that's just something that we had to do first. So based on the results in the table, it looks like the pre-construction conditions are greater than the post-construction conditions because the peak flow rate and the runoff volume are more. However, when you export the hydrograph data in table format, which is converted into a chart here, you can see all the points on the post-construction hydrograph that exceed the pre-construction hydrograph, which are highlighted in yellow. You should similarly inspect all storm events this way because, again, this is just the projected 100-year design storm. So this example dispels the common misconception that the reduction of impervious surface will automatically meet the quantity control requirements. Municipal review engineers must require that the design report include hydrologic modeling and hydrographs, even when the design engineer claims there is a reduction of impervious surface by the proposed development. Moving on from option 1, we will not be discussing option 2 because that was previously covered and not commonly used. So that leaves us with the last option, the most common option, option number 3. This option requires the use of BMPs to reduce the post-construction peak flows to 50, 75, and 80% of pre-construction peak flows for the current and projected 210 and 100-year storms, respectively. And even though this is the most common option, we still see a lot of mistakes. So let's go over it. So listed here are the various BMPs in chapters 9 and 10 of the BMP manual that can be used to provide quantity control. Please note that all of these BMPs are considered GI, which is a requirement to meet the quantity control standard. Additionally, chapter 11 BMPs, which are not listed here, cannot be used to provide quantity control without a waiver or variance because they are non-GI. So that includes BMPs like extended detention basins and non-GI wet ponds. Now, as I mentioned earlier, the stormwater report shall provide routing calculations for all subdrainage areas for all design storms. And the reviewer should check the unit hydrographs, the rainfall depths and distributions, the CN values, and whether or not they were averaged, and the times of concentration. You should also check the summary to verify if exfiltration was used, which is shown as discarded, what the primary outflow is, which is the flow ultimately coming out of the BMP, and if the smallest orifice is 2.5 inches or larger, which is a requirement of 7:8. Now, as a reminder about exfiltration, infiltration of the entire 210 or 100-year storm is allowed only when the existing site conditions are such that no runoff leaves the site for the pre-construction condition scenario, thereby constraining the design to infiltrate 100% of the volume produced by the post-construction condition for the same design storm. In this case, the maximum storm that can be entirely infiltrated is the largest storm event with no runoff leaving the site in pre-construction conditions. Exfiltration is also allowed if the volume of stormwater runoff to be fully infiltrated is required by law or rule implemented by the Pinelands, the Highlands, or any other stormwater review agency with jurisdiction over the project. It's important to remember that if any of the BMPs will infiltrate runoff into the subsoil, a groundwater mounding analysis is required to determine the impacts on the groundwater and adjacent structures. Therefore, if the design engineer is proposing an infiltration BMP, but has not provided a groundwater mounding analysis, the reviewer shall ask the design engineer to provide it. Now, often, the groundwater mounding analysis will show the mound rising above the bottom of BMP, which means that the hydraulic conductivity will be decreased from the original design value. If this is the case, the routing calculations must also be adjusted to reflect this new lower exfiltration rate. The primary peak flow rate will then need to be rechecked, and if the peak flow rate is too large, the basin size and/or outlets will need to be adjusted. The point being, it can become a very iterative process to get the mounding and the routing to work together. And one last note about stormwater runoff quantity control. small-scale GI-BMPs in Table 5-1 of 7:8 can be used to provide both quality and quantity control, typically with a contributory drainage area limit, while large-scale GI-BMPs in Table 5-2 of 7:8 can be used to provide only quantity control without a contributory drainage area limit. For example, a small-scale infiltration basin that is designed to have the first outlet at the water quality design storm elevation may also have additional outlets, to include orifices or weirs, to attenuate runoff from the larger 210 and 100-year storms. The important part is that the detention components must be situated in the same location as the BMP, either above the water quality design storm elevation or below the surface. A BMP with a detention component located downstream, outside of the basin's footprint, does not meet the design requirements as stated in the BMP manual. The next thing that you, the reviewer, need to check is stormwater runoff quality control. Shown here are the design and performance standards for stormwater runoff quality control per 7:8. These standards are applicable when the major development results in an increase of 1/4 acre or more of regulated motor vehicle surface. So, for new development, the proposed design must remove 80% of total suspended solids, or TSS, for the stormwater runoff generated from the water quality design storm from the net increase of motor vehicle surface. And although there is no numerical target, the stormwater management measures shall also be designed to reduce to the maximum extent feasible the post-construction nutrient load. So let's talk about TSS for a second, just so everyone understands what it physically is. It's a measure of the concentration of solid particles that are suspended in water, as opposed to dissolved. This includes things like sand, silt, and clay, organic matter such as leaves, and just general trash from the site. It's the things that make the water look turbid or cloudy. Additionally, per the stormwater FAQs on the DEP website, for redevelopment of existing impervious surfaces, the required TSS removal rate is the greater of the TSS removal rate of the existing stormwater treatment system, or 50% TSS is required. It's important to note that these removal rates apply to each subdrainage area unless the runoff converges on site to one point of analysis. So what does this mean? This means that if all the runoff converges to one point of analysis, the design engineer may choose to overtreat some areas, say to 90%, and undertreat other areas, say to 50%, to achieve a weighted average of 80% TSS removal across the site. However, again, removal rates must be achieved for each point of analysis. You cannot average different points of analysis. Additionally, pursuant to the flood hazard area rules, runoff from the water quality design storm discharge within a 300-foot riparian zone must reduce TSS by 95%. Now, why is this? Because 300-foot riparian zones are associated with Category 1 waters to include all tributaries upstream in the same Huck 14 watershed. And Category 1 waters have the highest classification in New Jersey. They're waters that have exceptional significance because of their ecological value, recreational value, water supply value, or aesthetic value. So it's important we keep them clean. Now, what exactly is regulated motor vehicle surface? Because remember, the quality control standards apply to the increase of regulated motor vehicle surface. Well, per 7:8, it is defined as a net increase in motor vehicle surface, which is any surface, impervious or pervious, that is intended to be used by motor vehicles and/or aircraft and is directly exposed to precipitation. It also includes the total area of motor vehicle surface that is currently receiving water quality treatment either by vegetation or soil, by an existing stormwater management measure, or by treatment at a wastewater treatment plant, where the water quality treatment will be modified or removed. Now, an important note about pervious paving. So yes, a pervious paving system can provide TSS removal. It's a BMP. However, it still needs to be considered regulated motor vehicle surface when looking at the quarter-acre increase. And it also needs to be assigned a CN of 98 for quantity purposes. So you, as a reviewer, should check both things. Now, looking at roof runoff. Roof runoff is considered clean because it is not typically a significant source of TSS. That is, unless it commingles with other dirty runoff. However, it can be a significant source of nutrients. And because of this, roof runoff may require pretreatment, like we discussed during Module 2 and in the BMP manual. The point being, this is something you have to consider as a reviewer. How is the roof runoff being handled? Now, let's talk a little bit about what the water quality design storm is. We keep mentioning it, but what is it? Well, it's a design storm based on historic data that is specific to New Jersey. It's a relatively common and intense storm that introduces TSS into our collection systems and waterways. And more specifically, it is a nonlinear rainfall distribution resulting in 1.25 inches of precipitation in 2 hours. And let's take a look at what that means exactly. So as I mentioned, the water quality design storm is 1.25 inches, shown on the y-axis, over 2 hours, shown on the x-axis. But remember, in addition to the rainfall depth, we need the rainfall distribution, which is how the rain falls. And the graph on this slide is the cumulative distribution curve for the NJDEP water quality design storm. It has a nonlinear distribution with a higher intensity in the middle, meaning that the rainfall starts light, gets heavy in the middle, and ends light as well. This nonlinear distribution is conservative because real storms have bursts of intensity, and this creates a higher peak flow rate. So listed here are the various BMPs in Chapter 9 of the BMP manual that can be used to provide quality control. Please note that all of these BMPs are considered GI, which is a requirement to meet the quality control standard. Additionally, Chapters 10 and 11 BMPs, which are not listed here, cannot be used to provide quality control without a waiver or variance because they are large-scale and/or non-GI. So that includes BMPs like constructed wetlands and extended detention basins. Now, the BMP manual is extremely important here because there are specific design criteria that need to be met for a BMP to merit the approved TSS removal rate. And you, as a reviewer, need to be checking this criteria. I also think an important distinction for grass swales needs to be made because I saw a lot of people get this wrong on quiz 2, actually. So in general, there are 2 types of grass swales, right? Those being used as a BMP per Chapter 9.3, meaning you can use it for water quality control, and those not being used as a BMP. So your typical diversion swales, where you're not trying to get a quantity, quality, or groundwater recharge benefit out of it. So in quiz number 2, there is a question about which BMPs require a maintenance plan. The answer is all of them, right? But I think people tend to forget that a grass swale can be used as a BMP when designed in accordance with the manual. So I just wanted to make that a quick point. A grass swale can be used to provide 50% TSS removal. So let's take a quick look at the TSS removal rates and the phosphorus and nitrogen removal rates for various BMPs. As a note, the nutrient removal rates can be found in Chapter 4 of the BMP manual. And the reason we look at phosphorus and nitrogen is because they are both the most common nutrients and the most detrimental. They're naturally present in soils, plants, and organic matter, and stormwater runoff easily picks them up. Now, sometimes BMPs are used in series, meaning one right after another, like a treatment train, to obtain the needed TSS removal rate. Because remember, not all BMPs give 80% TSS removal, and Category 1 waters require 95% TSS removal. And some jurisdictions may also require a higher removal rate. So the equation in bullet 3 can be used to determine the total TSS removal rate, with R being the total rate, A being the rate of the first BMP, and B being the rate of the second BMP. And this equation is also in 7:8. Now, here are some important notes when using BMPs in series. Number 1, BMP shall be arranged from upstream to downstream in ascending order of TSS removal rate. Number 2, in ascending order of nutrient removal rate. And number 3, by relative ease of sediment and debris removal. Additionally, you cannot use two of the same BMPs in series because the downstream one will not be as effective. So lastly, here's an example of using a vegetative filter strip followed by a small-scale infiltration basin. It would give you a total removal rate of 92%. As mentioned before, nutrient removal is required for all major developments and shall be addressed to the maximum extent feasible. Some BMPs have nutrient removal capabilities, but the best way to handle nutrient removal is by source control. And as mentioned before as well, BMP shall be designed in accordance with the BMP manual because there are specific design criteria that need to be met for a BMP to merit the approved TSS removal rate. However, alternative designs may be submitted for approval if the design engineer can provide documentation demonstrating capability of alternative removal rates and methods. And these approved alternatives must be submitted to DEP. So in summary, when reviewing the stormwater runoff quality component of a project, the reviewer must, number 1, ensure water quality BMPs chosen are adequate to achieve required TSS removal rate. Number 2, ensure small-scale GI BMPs from Table 5-1 are used unless a waiver or variance is obtained. Number 3, ensure runoff from all drainage areas requiring water quality treatment is being collected and treated. Number 4, ensure BMP design meets criteria under applicable BMP manual subchapter. And last but not least, ensure a deed notice of the stormwater BMP is submitted for approval and recorded in County Clerk's office prior to the commencement of construction. Now, there are some general design criteria for all water quality BMPs. This includes drain time and seasonal high water table separation. So all BMPs must drain within 72 hours. Unless they are subject to pedestrian traffic, then the drain time is reduced to 24 hours for safety reasons. And most BMPs require 2-foot separation from the seasonal high water table. However, under-drain BMPs only require 1 foot, and MTDs are subject to the manufacturer specifications. And here are the most commonly used water quality BMPs. We have small-scale infiltration basins, small-scale bioretention systems, GI MTDs, grass swales, and pervious paving systems. And we'll take a closer look at some of these. So taking a closer look at the small-scale infiltration basins chapter, which is chapter 9.8 in the BMP manual, the first page is a summary page. The paragraph at the top describes how the BMP functions to remove pollutants, and the table right below that tells you which performance standards you can meet with this BMP. So in this case, you can use the small-scale infiltration basin to meet the GI requirement along with water quantity, quality, and groundwater recharge, and you get 80% TSS removal. Also, please notice that the chapter title is green. So this is because all of Chapter 9 is green, Chapter 10 is blue, and Chapter 11 is black. And this was done to make the amended BMP manual more distinctive from the previous versions. So because small-scale infiltration basins can be used to meet pretty much every standard, and they're a relatively shallow BMP, they're incredibly common. So let's talk about some specific design criteria for these BMPs, things you should look for. So first and foremost, a small-scale infiltration basin must be designed to infiltrate the entire water quality design storm, hence the name, infiltration basin. It must also meet the infiltration permeability testing requirements in accordance with Chapter 12 of the BMP manual, which Lisa discussed during Module 2. And the maximum depth of the water quality design storm in the basin is 24 inches. And this is what really dictates the footprint of your basin. Additionally, the basin must include a 6-inch AASHTO M6 or ASTM C33 sand layer. The bottom basin must be level and uncompacted, so the soil erosion and sediment control plan should address how they plan to achieve this. Subsurface infiltration basins require 80% TSS pretreatment, and the design hydraulic conductivity of the most restrictive soil horizon below basin bottom shall be between 0.5 and 10 inches per hour. So these are all things to check for in your review. You want to make sure they have all these things. Now, what should you not see? Well, you should not see basins designed for water quantity control, but no outlet structure. So how are they controlling the larger storms? You should not see under drains or liners. Again, the water quality design storm needs to infiltrate. You should not see topsoil or vegetation because it's a sand bottom basin. And you should not see standing water 72 hours after the precipitation stops because this will lead to impaired basin function and even failure. Now, here's a beautiful example of 2 small-scale infiltration basins. Do you want to guess which one is functioning correctly? And hopefully you all said the top one. So the bottom one has established vegetation and ponding by the head wall. So ponding like this is going to affect the hydraulic performance of the basin. It may lead to structural concerns with the head wall because of seepage and erosion. And this stagnant water becomes the perfect location for mosquitoes and algae. So all things we want to avoid. And how do we avoid this? Post-construction testing to ensure it was built correctly and proper maintenance. So moving on to small-scale bioretention systems, which are also common because they can be underdrained to not infiltrate. So again, shown here is the summary page. And notice that it says 80 to 90% TSS removal. Why is this? Well, because the TSS removal rate varies based on the soil bed depth and the type of vegetation. And it makes sense that a terrestrial forested community, aka trees, provides more TSS removal than site-tolerant grasses, aka shrubs and perennials. So you as a reviewer need to make sure that the chosen TSS removal rate lines up with their BMP cross-section and the landscape plan. Now, as mentioned earlier, small-scale bioretention systems can be designed to infiltrate or be underdrained. They can also greatly vary in size from small rain gardens to full-on basins. So, one of the most important components of a bioretention system is the engineered bioretention soil. There needs to be a certain depth, like we just talked about, and the soil itself shall have a certain amount of sand, silt, clay, and organics, again, to merit that TSS removal rate. And this soil mix should be specified on the plans, maybe on the landscape plan, maybe on the detail sheet, but it should be there. Small-scale bioretention systems also have specific design criteria for water quality depth, which is 12 inches instead of the 24 inches we saw for infiltration basins, bottom slope, and density of vegetation. And all of this can be found in Chapter 9.7 of the BMP manual. And you, as a reviewer, need to make sure this is met. All right, so before we finish this portion of the presentation, let's talk about infiltration criteria a little bit. Now, this criteria applies to any BMP designed to infiltrate runoff. This includes small-scale infiltration basins, dry wells, small-scale bioretention systems without an underdrain, and small-scale sand filters without an underdrain. Now, let's take a look at what some of those criteria are. First and foremost, the soil permeability must be tested. It cannot be assumed. It must be tested in accordance with Chapter 12 of the BMP manual. After it's tested, a factor of safety of 2 must be applied to this field permeability to get the design permeability. And then this design permeability must be between 0.5 and 10 inches per hour. If it is less than 0.5, you cannot use an infiltration BMP without soil amendments. Once again, you must have at least 2 feet of separation from the seasonal high water table, maybe 1 foot for some of those under-drain BMPs, and the seasonal high water table elevation must be proven via soil testing as well. And after you know the design permeability rate and the seasonal high water table elevation, you must assess groundwater mounting impacts. So these are all things you should see as part of the stormwater management report for infiltration BMPs. Soil testing to determine the seasonal high water table and the infiltration rate, and a groundwater mounting analysis. If the design engineer did not provide this, you need to ask for it. Lastly, when reviewing plans, as mentioned before, there should be a soil erosion and sediment control plan addressing sediment and compaction impacts during construction, and there should be language requiring post-construction soil testing. 2 very important things. And that's the end of this presentation. I know that was a lot, so thank you for your attention. And if you have any questions, please feel free to reach out to the group or to Manesh or to myself, and our emails are on the screen. And before we wrap up this portion of the presentation, if you have any questions, please add them to the chat. Changi will continue to respond to them as we move along with Module 3. And meanwhile, up next is Lisa Schaefer, and she will continue to discuss how to review a project for compliance with design criteria in the BMP manual.
Thank you, Rachel. We will take a break, and please come back at 2:30. Thank you.
Okay, welcome back from the break, everyone. It's now 2:30, so we will continue on. All right, so I'm Lisa Schaefer. I'm sure you all know me by now, and I want to say thanks to Rachel and Manesh. I'm sure the reviewers appreciate your coverage of the stormwater design and performance standards, and also that those who are not reviewers have a better understanding of just how important it is to properly review projects for major development. This presentation will hopefully add a bit more to a reviewer's skill set. So here's the goals of this presentation. Okay, and by these, I mean that we want reviewers to be able to identify the design and performance standards that must be met on site. Okay, what to check in sizing calculations for MTDs. And lastly, how to review groundwater recharge requirements in addition to making sure the safety standards are met. All right, so let's start with the first goal, review BMPs for compliance with the BMP manual design criteria. In Module 1, you learned that the BMP manual chapters are arranged in accordance with the order of the BMPs that are listed in tables 5-1, 2, and 3 found in the rules. So on the next few slides, the list of the respective chapters and the corresponding table from the rules are listed side by side for your reference. All right, so as Rachel indicated before, each subchapter of chapters 9, 10, and 11 has a section titled Design Criteria, and a BMP needs to be designed to comply with all of the specified design criteria. Otherwise, it doesn't merit the approved TSS removal rate required to address water quality. So let's look at the kinds of BMPs included in the stormwater management rules. On this slide are the GI BMPs. Some can be used for water quality, provided the TSS removal rate listed in the second column of Table 5-1 is not 0. All right, which is the case for 7 of the 10. Some can be used for quantity control, as noted in the middle column. Okay, and then there are those that can be used for groundwater recharge as listed in the columns on the right. Now that's provided the 2-foot separation from the seasonal high water table is provided as measured from the bottom elevation of the lowest component in the BMP. All right, so here are the BMP chapters for GI BMPs that can be used for stormwater runoff quantity control. The first 3 are basically the big brother versions of the small scale systems found in chapter 9. Take note that if you want to use these BMPs here, all right, for water quality or groundwater recharge, then you will need to make sure there is a waiver or variance that's properly, put in place. And Manesh will go over variances in Module 4. Now, the Table 5-3 BMPs are not GI BMPs, and you will always need to obtain a waiver or variance before you can use any of these for meeting the water quality or quantity control or groundwater recharge requirements. So here's some important highlights of the design criteria for some of the BMP chapters. So you're going to obviously go to the full chapter for additional details. So for cisterns, if you want to design a cistern, the stormwater volume needs to be at least that of the runoff generated by the water quality design storm, but the cistern also needs to be emptied by the reuse demand within 72 hours. For dry wells, the design volume of a dry well cannot exceed the runoff volume from the water quality design storm. Now, although a dry well cannot be used to treat runoff from motor vehicle surfaces, it can prevent clean roof runoff from being commingled with the dirty runoff from motor vehicle surfaces, such as a driveway, so that way it can reduce the size of a BMP needed for water quality treatment. And in pervious paving systems, the storage volume needs to be at least equal to the runoff from the water quality design storm. Now, although there's no surface runoff from a pervious paving system, you need to use 98 for the curve number so that the amount of precipitation falling on the pervious paving surface can be calculated. Small scale infiltration systems, all right, so for an infiltration BMP means one designed to infiltrate runoff into the soil. So if the designer calls the BMP an infiltration BMP, it cannot be designed to have an underdrain system to direct runoff from being transmitted to the subsoil. Also, an infiltration basin cannot have vegetation on the bottom of the basin. So if it has, it cannot be recognized as an infiltration basin. Small scale sand filters, all right? So if they're designed or if they're intended to meet the GI standards, they also cannot be designed with an underdrain for the same reason. Vegetative filter strips. Well, not every piece of a vegetated area can be recognized as a vegetative filter strip. Only those areas that are designed and maintained strictly in compliance with the design criteria of the vegetative filter strip chapter can have the TSS removal rate listed in the chapter. And the TSS removal rate and the filter strip length depend on the vegetation, the soil type, HSG, and slope. There are figures and curves that you can use to find the TSS removal rates associated with these 4 parameters. So we've seen more developments using GI wet ponds to meet the water quantity control requirement. So let's discuss all wet ponds in a bit more in detail. All right, we're going to start with the non-GI wet ponds, which can be used for water quantity and quality only when a waiver or variance from NJAC 7:8-5.3 is obtained. They have a minimum 0.25 acre permanent pool surface, and the minimum ratio of the permanent pool volume to the water quality design storm volume is 1:1. They also have a minimum drainage area of 20 acres, and they require very low permeability soils or an impermeable liner. Now, for GI wet ponds, they can be used for water quantity, and they can be used for water quality only when there's the waiver or variance from this part of the rules. So in addition to the design criteria for non-GI wet ponds, GI wet ponds need to have at least a 10-foot wide area of native vegetation along at least 50% of the shoreline. They also need to include a stormwater runoff retention component designed to capture stormwater runoff for beneficial reuse, such as irrigation. Now, the volume available for beneficial reuse shall be equal to or greater than 1.25 inches of rain falling over the drainage area of the GI wet pond. And stormwater reuse demand is based on the lowest volume need that would occur over any 3 consecutive days during the year. Okay, now beneficial reuse shall not cause the water level to be less than the permanent pool water level, and GI BMPs that infiltrate the water quality design storm runoff into the subsoil cannot provide water quality design storm runoff to the GI wet pond for beneficial use. So the beneficial use of a GI wet pond is often to provide landscape irrigation. The method to estimate irrigation use shall be based on some reasonable assumptions. So the designer cannot randomly assign a value like 1 inches per acre per day to calculate irrigation use. So the NRCS has published a New Jersey irrigation guide, which provides one method to estimate the irrigation need. So if the designer wants to use another method, the submission will need to provide a well-recognized publication showing the method and the variables that were used in the calculations. So we'll work on guidance for those situations, but for now, we can consider them on a case-by-case basis. And obviously, municipalities should contact us for assistance in making those determinations. All right, so additionally, I want you to realize that the available water capacity can be found from the web soil survey. Use the weighted average within the effective root zone depth of the landscaping vegetation. All right, now, the vegetation all right, must consume or meet the irrigation needs. So they have to equal, and it's for a 3-day period. Also, evapotranspiration of the landscaping areas has already been considered in the consumptive use, so you would not count it again. And lastly, evaporation lost from the wet pond surface can be counted as part of the beneficial use. All right, so now let's move on to the safety requirements, which are found in NJAC 7:8-6.2. So designs must follow the stormwater management rules regarding the trash rack and overflow grate specifications. So this is also included as text within the illustration shown here. It's in the BMP manual chapters, usually under the outlet structure information, and this depicts the requirements stated in the rules. So when a wet pond or other BMP that has a permanent pool of water that's greater than 2.5 feet in depth, all right, you also need to make sure the design follows the rule requirements for this safety ledges. Okay, if not, then address the lack of this information in the review letter. All right, so now let's talk about the design that includes an MTD. So some of this information may be a little repetitive, but we often see incorrect sizing calculations in our reviews. So therefore, we're hoping that this emphasis will inspire a little extra attention be given to MTDs proposed for a project. All right, so under the stormwater management rules that went into effect on March 2nd of 2021, there are two major categories of MTDs. Green infrastructure manufactured treatment devices and non-green infrastructure MTDs. A GI MTD shall infiltrate runoff into the subsoil and or treat stormwater runoff through filtration or treat stormwater runoff through filtration by vegetation or soil. An MTD that uses a biofiltration media and can be configured above ground and incorporates, say, a tree box, a planter box, or shrubs, or so forth, would meet the GI definition. Any MTD with biofiltration media that would be placed below ground, say in a vault without any vegetation, can be considered to be GI for New Jersey purposes only if the device infiltrates stormwater into the subsoil. So furthermore, the below ground device or vault would need to meet the NJDEP BMP manual soil testing conditions of Chapter 12, which means the soil below the MTD must meet the minimum tested infiltration rate of 1 inch per hour, have at least 2 feet of separation from the seasonal high water table, and runoff would infiltrate into the subsoil. So of course, the other category of MTDs is the non-GI MTDs. So they neither infiltrate runoff into the subsoil nor treat stormwater runoff through filtration by vegetation and or soil. So just a reminder that if the design proposes to incorporate MTDs to meet the water quality design and performance standards, then the designer must incorporate GI MTDs into the design unless a waiver or variance for using non-GI MTDs is granted. So for all MTDs proposed to meet water quality in a project, they must be verified by NJCAT and certified by NJDEP. So devices that aren't currently certified cannot be used to meet the design and performance standards. You're going to follow the sizing calculation that is in the certification letter for that particular MTD. All right, they're all listed here at this link on the slide. But take note that the maximum contributory drainage area of a GI MTD is 2.5 acres. So remember from Module 2 that contributory drainage area is defined as the area from which stormwater runoff drains to a stormwater management measure, not including the area of the stormwater management measure itself. Okay, so we want to emphasize that the review engineer must read the certification letter before wrapping up the review. This letter provides the calculation method to size and select appropriate models of a particular MTD. The maximum treatment flow rate is calculated based on peak flow rate from the impervious surfaces during the water quality design storm. Now, the certification letter also has other criteria and conditions of using the certified MTD. So one of the MTD letters states that the inflow for the MTD can only be a single pipe. So again, if the site plan shows that 2 pipes direct flow into the MTD, it's not designed in accordance with the certification letter and cannot receive the TSS removal rate that is stated in the certification letter. So because only specific MTD models from the MTD manufacturer were tested, the manufacturer's other models not listed in the certification letter, even though they might be the same brand name or type, they cannot be used to meet the water quality design and performance standards. Now, you've heard this before, but MTDs were tested under specific configurations and installation specifications. Those that deviate from the configuration or installation specifications cannot be used to meet the water quality design and performance standard. If the sizing requirement in the certification letter indicates that the sizing is based on the maximum treatment flow rate, or MTFR, and maximum flow impervious area, the model that is selected shall be based on the flow rate and the drainage area, whichever results in the highest minimum configuration. So each certification letter has a sample sizing calculation illustrating the choice of a particular model. All right, so now with regard to MTDs that were tested and certified that included the vegetation in the MTD, all right, you are going to see in the certification letter the language that is shown here. So one of the conditions requires the maintenance of vegetation cover at 85%. You will definitely need to see a maintenance plan that has preventative and corrective actions to maintain the vegetative cover at this level. You will also want to check the MTDs regularly to ensure the vegetative cover is maintained satisfactorily, especially say after a dry spell or a period of excessive rainfall. Now, there are other design criteria in the MTD certification letters that a design must follow in order to receive the TSS removal rate. So this is another sample of the language regarding a GI MTD that is underground. It needs to be designed to infiltrate the entire water quality design storm in order to be recognized as a GI MTD and receive the 80% TSS removal rate. So remember, MTDs are no longer sized using the rational method. All right, the stormwater management rules that were amended in July of 2023 specify that the NRCS methodology shall be used. There's an example, number 5-9 in Chapter 5 of the manual, that demonstrates the necessary calculation. So that means you're going to make sure the standard dimensionless unit hydrograph is used, right? You can't use Delmarva, and that the precipitation depth is based on the projected 2-year design storm. So remember to apply the future precipitation change factor from table 5-6 of the rules to either the 2-year NOAA precipitation data or to the county rainfall data to calculate the precipitation depth for the projected 2-year storm. This example is sizing an MTD using the NRCS methodology. All right, this example will walk you through what's now required. So we have a 0.26 acre paved motor vehicle surface with a slope of 5%. The rainfall depth for the projected 2-year storm, not story, is 3.84 inches, and the hydraulically most distant point to the inlet of the GI MTD is 110 feet. So when using the NRCS methodology, you need to calculate the time of concentration, for which we follow the method that's covered in example 5.1 in chapter 5 of the manual. And that example will also be on page 30, is on page 33. All right, it's also the formula that was on slide 29 of the calculations presentation. So as was stated earlier, we use P2 for the projected 2-year storm in the T sub C calculation for the water quality design storm. Of course, the drainage area is only a 1/4 acre or 0.26 acres here. So if you mistakenly use P2 from the current 2-year storm, it's probably not going to make much of a difference. But technically speaking, you use the projected 2-year storm in the TC calculation. All right, then we're going to calculate the maximum sheet flow length using the formula for the McEwen-Speece limitation that's found on page 24 in chapter 5. And in this case, it's equal to 909 feet. However, remember, the maximum sheet flow length should not exceed either that which we calculate under McEwen-Speece or 100 feet, whichever is shorter. So in this case, we're going to use 100 feet. So for our stated flow path length of 110 feet, that leaves just 10 feet of shallow concentrated flow. So doing all of this, T sub C is calculated to be 0.8 minutes. Now we're going to use the SCS standard dimensionless unit hydrograph with a shape factor of 484. And that's covered on page 27 of chapter 5 in the manual. So with all of this together, the modeling software calculates that the peak flow rate for the water quality design storm is 0.82 cubic feet per second. Now, so the next step would be to determine the size of the MTD. The selection of the model of a specific MTD listed on the department's webpage is based on the maximum treatment flow rate, or MTFR, for a hydrodynamic type MTD, or the maximum allowable drainage area, and the MTFR evaluation method per the certification letter for the filtration type MTDs. So you're going to look at chapter 9.5 for GI MTDs and chapter 11.3 for MTDs that are not certified as GI infrastructure for this calculation. All right, so we have a table here. It's showing various models of a hypothetical GI MTD, and we have the maximum treatment flow rate and the maximum allowable drainage area associated with each of these models. So both are going to be used to size the model. And if we look at the third column, the motor vehicle surface is 0.26 acres in size. So that means we cannot use model M1 nor M2 because the area we need is larger than the maximum drainage areas allowed for these two models. So that means we're going to check the MTFR for the remaining models in the table. Now, the water quality design storm peak flow rate for the motor vehicle surface was calculated to be 0.82 CFS. Only model M7 has an MTFR that is greater than the calculated peak flow rate. So therefore, we have to select M7 as the model for this project as it has the highest minimum configuration. Okay, so far, I've covered BMPs that should be designed to, you should check your design to make sure they meet the BMP manual. All right, Rachel covered that you can use multiple BMPs in series when necessary, and a bunch of these other things in terms of the infiltration BMPs. And we didn't cover it today, but detention BMPs must calculate detention time correctly. Okay, and of course, the MTT design uses the NRCS methodology. All right, now, if you're in a situation where you need to swap out an MTD that, you're revisiting a project, okay, and you need to swap it out for a second one, please feel free to reach out to us if you're unsure about the sizing. We've had some instances, such as one where someone went from a filter type to a hydrodynamic one, and unfortunately, too small of a model was selected, and that resulted in water quality issues and flooding. Okay, so with that being said, it's time to go into groundwater recharge. All right, so from the overview presentation, Peter covered the rule requirements found in NJAC 7:8 at 5.4 B1, and it's the two Romanettes 1 and 2, which require the project either demonstrate through hydrologic and hydraulic analysis that the site and its stormwater management measures maintain 100% of the annual pre-construction groundwater recharge volume for the site, or infiltrate the difference in the projected 2-year storm runoff volume. So if the option to infiltrate the difference is selected, it's a relatively simple calculation, but it means a larger infiltration structure is needed, and that could mean a greater risk of failure, as well as a larger groundwater mound in the hydraulic impact analysis that is required. Okay? So, and the review would make sure that the calculations use the NRCS methodology, show both the pre and post-construction projected 2-year runoff volumes, and the curve numbers and time of concentrations should match the quantity and quality calculations used elsewhere in the modeling. All right, so let's just do a quick example. So for this site, I've included the NOAA rainfall depth, the future precipitation change factor for Somerset County, and the depth of precipitation for the projected 2-year design storm. So with the precipitation depth, okay, of 3.93 inches, the projected 2-year storm will produce an increase in runoff volume for the post-construction condition of 17,886 cubic feet, shown here in the lower table. So to comply with the rule requirement, this is the target the design must achieve, provided it's designed in accordance with the B&P manual. Okay, so we are going to move on. If instead you select the first option, which maintain 100% of the pre-development groundwater recharge, you must use the groundwater recharge spreadsheet. So the reviewer will check both worksheets, which are the inputs for the pre and post development conditions that are then used to calculate the deficit, and then the evaluation of the proposed BMP or BMPs. All right, we'll start with the second worksheet. Okay. All right. So here's the first page of the groundwater recharge spreadsheet, which is called the annual recharge worksheet. The orange shaded areas are for the user inputs. The gray are the outputs. So let's look at the inputs that are required. All right, we're going to note that the infiltration is not the same as groundwater recharge. So infiltration is just getting runoff into the subsoil. But for groundwater recharge, the runoff needs to not only get into the subsoil, but it has to pass the root zone. So for different soils, there are different depths of root zones. So therefore, the soils in this spreadsheet play an important role in the calculation of annual recharge and the recharge provided by the BMP. So I want you to notice that the total area, 10.4 acres, okay, matches from pre to post. Right, we'll get to the blue rectangle over here in just a minute, but let's just discuss some of the other inputs in these boxes. All right, so the spreadsheet assigns annual precipitation based on the municipalities, so be careful when you're selecting your site. All right, as stated earlier, the volume of groundwater recharge is the runoff infiltrated into the subsoil and passed through to the root zone. In the spreadsheet, the land cover is used to determine how much runoff is infiltrated into the subsoil, and then the soil series is used to determine the depth of the root zone. All right, the spreadsheet will calculate the pre-development and post-development annual recharge. So the difference between them is the annual recharge deficit created by the proposed development. So here's some tips when using or reviewing the inputs of the spreadsheets. All right, the land cover you select for use in the sheet should also be reflected in the plans and hydrologic computations. And you're going to also have to know the acreage and the soils information. The sum of the acreage for all of the pre-construction land segments has to equal the sum for the post-construction land segments. So there's also, we have a question at times about the soil in the inputs. You can find the soil series from the Web Soil Survey, and it's on the soil information tab where you find, the hydrologic soil groups of this site. But in the event that the Web Soil Survey does not provide the soil series, you may use the default values in this from Chapter 12. They're found in Table 12-2, and that's on page 10. So for HSG A soils, the default is Fort Mott, and it's Nixon for HSG B. But note that the default C soil in the past was Venango, but it's been updated to Reddington. And also, we don't just use D soil to represent the soil series without recharge. The default D soil should be the soil series from the groundwater recharge spreadsheet that results in 0 groundwater recharge. So when you click down the list of the soil series in the spreadsheet, you can just find one and use it. Just make sure it shows zeros. All right, if the land cover is impervious surface, it doesn't matter what soil series you use, since the program automatically assumes no recharge on an impervious area. So once you have all of the land segment areas and land cover selected for the soils present, the worksheet calculates the deficit that will be created by the proposed project. Here, it's 103,435 cubic feet shown in the red rectangle. So now we're going to go on to the second worksheet, which is here. It's labeled BMP calculations, and we're going to evaluate whether the proposed BMP adequately addresses the deficit that's created by the proposed development. So this is what the BMP calculation worksheet looks like. And just like the first one, the orange areas are for your inputs and the gray areas are the outputs. So the red text shown on the right, all right, it shows the status of whether or not the calculations are correct. The gray buttons on the left, okay, those are solve for ABMP to provide VDEF, solve for DBMP to provide VDEF, and default VDEF and AIMP. They're not really used in this spreadsheet when you're using the actual BMP design parameters to check whether the annual BMP recharge volume is equal to or greater than the post-development deficit recharge. Okay, so next, we're going to take a look at this red box, all right, which is for the input to denote the BMP's location. Since each different soil has a different root zone, the soil at the location of the BMP will be an important factor to determine the amount of runoff in the BMP that can pass the root zone. Okay, therefore, the BMP location shall be the land segment where the BMP is to be located in the post-construction site, all right, as you input it on the other sheet. If the location of the BMP is not input, this worksheet will default to a value of 0, by which it uses an average root zone depth of all the soil series in the post-construction condition to calculate the annual BMP recharge. So we're going to address the other BMP design criteria parameters, these and all these red boxes, in just a moment. But first, I want to talk a little bit more about the BMP location segment, seg BMP. All right. So the variable seg BMP is the post-development developed site segment in which the proposed recharge will be located. I just said that. All right. So, and you can, specify on site where it's going to be. But if you don't know where it's going to be, you set it to 0 and it will do the averaging. But for porous pavement, the segment shall be the impervious area in the post-development. All right. So let's talk about the variables shown from the other red boxes that were on the previous slide. All right, VDEF, all right, is the post-development deficit recharge by default, and it is the post-development annual recharge deficit from the first worksheet. However, there are some instances in which it can have different values. So for example, if you have 2 BMPs, then each BMP will be responsible for a portion of the annual deficit from the worksheet. So when this happens, you'll need 2 workbooks so that you could split the annual recharge deficit between those 2 BMPs, and you're going to separately calculate the BMP recharge provided by each of those BMPs in the corresponding workbook. Okay, So AIMP is the post-development or post-D impervious area, or the targeted impervious area. It's the size of the impervious surface contributing the runoff into the BMP. In some situations, not all impervious surface will contribute to a specific BMP. So you might have runoff from part of an impervious surface that's directed to a wet pond, and that doesn't provide recharge. Okay, so in another situation, you may have more than one BMP, such as 2 infiltration basins in 2 locations or have different soils. So then you're going to use more workbooks and split the impervious surface between these locations in their respective workbook. And then you're going to add the annual BMP recharge volumes together to check if it's equal to or greater than the deficit originally calculated for the entire site. Now for the parameters for the upper left corner of the BMP worksheet, okay? A BMP is the BMP area for infiltration. The sides of the BMP, which are quite often sloped, are not counted for infiltration. Therefore, they cannot be counted for groundwater recharge. DBMP represents the BMP effective depth. So it means the maximum equivalent water depth achieved before overflow begins. If the BMP is filled with stone, of course, we have to factor the effective depth by the porosity of the fill material. And if the BMP has a slope, such as a bioretention swale, we're going to have to make some adjustments to the effective depth. We're going to do that by dividing the storage volume by the value for ABMP to get the averaged DBMP. All right, and then I do have a little bit more about the other inputs on the next slide. All right, so DBMPU is the vertical distance from the vegetated ground surface to the maximum water level of the BMP. All right, it's positive if the maximum level is below the ground surface, okay, if you're going down into the BMP. It's negative if it's above the ground surface. So also we have DEXC, vertical distance from the vegetated ground surface to the bottom of the BMP. All right, that's confusing as all. So we're going to look at some different design scenarios to clarify the values that we use for these particular variables, okay? So, all right, this is an example of a BMP that has a vegetated bottom. So it represents recharge BMPs like bioretention basins. The parameter dBMPU is the depth to the upper level in the BMP. In plain language, it's the vertical distance from the vegetated ground surface to the maximum water surface level in the BMP. And if the vegetated ground surface is below the water surface, the value is negative, like the figure that we see here. Now, the second input is the DEXC. That's the depth of the lower surface of the BMP. So in plain language, it's the vertical distance from the vegetated ground surface to the bottom of the BMP. In this case, the vegetated ground surface is at the bottom of the BMP. So therefore, DEXC is 0. All right, and I'll get to others where there's only vegetation adjacent to the BMP in just a moment. All right, in this figure, this one shows another scenario where the bottom of the BMP is not vegetated. So that represents our infiltration basins and sand filters, okay, designed to infiltrate. In this scenario, the vegetated ground surface, or sorry, vegetated ground level is the ground level surrounding the BMP. dBMPU is the vertical distance from the vegetated ground surface to the maximum water surface level in the BMP. And in this scenario, it's positive since the vegetated ground is above the maximum water level. All right, the DEXC is the vertical distance from the vegetated ground surface to the bottom of the BMP, which is the full distance from the bottom BMP of the BMP up to the ground level surrounding the BMP. And lastly, we have situations where the BMP is underground, like the storage bed and a pervious pavement system or an underground infiltration basin. dBMPU is from the top of the gravel layer where the runoff is stored to the top of the ground level, and the value is positive. Now, if the maximum water level in the gravel storage bed is not all the way up to the top of the gravel storage bed, then dBMPU will be measured up to the maximum water level, or from the maximum water level to the ground level. The DEXC will be the distance from the bottom of the gravel storage bed up to the ground level. All right. So let's look at an example. We have a BMP in which the sender, shown here in yellow, is designed to infiltrate stormwater over an area measuring 6,000 square feet. All right, this is a sectional view of the infiltration basin there. All right, so there's no vegetation at the bottom of the basin. The dBMP is the maximum water level before the water begins to overflow. So from the figure, the maximum water level during the water quality design storm is at an elevation of 12.5 feet. Now, normally you have an orifice set at this elevation, so normally the dBMP would have been the distance between the maximum water level of the water quality design storm and the bottom. However, in this case, it's a little bit of variation. So from the outlet structure detail that was provided, we see the lowest orifice is set at elevation 13.36 feet, which is between the elevation of the water quality design storm and the 2-year storm. So in this case, the orifice is set at an elevation higher than the water level of the WQDS to capture more runoff in order to provide enough runoff volume to meet the annual groundwater recharge deficit. So knowing all of this, dBMP is therefore 13.36 minus 12, which is equal to 1.36 feet. So let's look at the BMP design inputs. dBMPU is the vertical distance from the vegetated ground surface to the maximum water level surface in the BMP. The vegetated ground surface in this case is not the top of the berm. It's the ground elevation surrounding the BMP, which is at an elevation of 15 feet. Since the maximum water level before overflow is at elevation 13.36, the dBMPU, that is, the vertical distance from the vegetated ground surface to the maximum water surface elevation in the BMP, is 1.64 feet. The DEXC for this BMP, since it has an unvegetated bottom, is the distance from the vegetated ground level to the bottom of the BMP. So that's 15 minus 12 feet, so our answer is 3 feet. So as we calculated before, the BMP effective depth, all right, dBMP, is the maximum water depth, which is the distance from the elevation of the first orifice to the bottom of the BMP. All right, but okay, it's here, shown here. The volume before the first orifice in this case was 59,400 cubic feet from the report. So we can use this volume to calculate a BMP, which is the BMP infiltration area. We know the effective depth is 1.36 feet. So the equation for volume of a BMP is the BMP area multiplied by the effective depth. So solving for area, that is volume divided by effective depth, that gives us a BMP is equal to 43,676 square feet. All right, so if this basin had been designed as a bioretention system, the value for DEXC would be 0, since the BMP in that case would have a vegetated bottom surface. But in this case, dBMPU would be negative 1.36 feet, okay? So, all right, so that is everything I have for that. And I want you to remind you about important rule requirements. You cannot recharge areas with high pollutant loadings nor industrial stormwater that is exposed to source material. So if you have a gas station, all right, and you're near the pumps, that should direct runoff away from any recharge BMP. Now, the design criteria from the applicable chapter must all be met. and groundwater mounting must also be addressed. So Peter will cover that next. So that's just about everything I have. All right, so we covered some highlights from some of the chapters along with tables 5-1, 2, and 3. We talked about the safety requirements, what is needed for a proper MTD design, and we covered groundwater recharge. All right, so I want to thank you very much for your attention. But please don't hesitate to contact us if you have any questions when you're conducting a review. We're always happy to help. Now, at this point, I'm going to ask Changyi if there's any remaining questions to be answered.
No, please continue. Thank you.
Okay. Well, next up is Peter Plianthos, and he'll be presenting the groundwater mounding analysis, which illustrates some interesting examples using the Hantush spreadsheet. So please stand by while I hand over control to Peter. Thank you, everyone.
All right, thanks, Lisa. I will now share my presentation. All right, just one more moment. And there we go. So hello, everyone. This is Peter Plianthos from the Municipal Stormwater Engineering Unit. In this presentation, we'll dive into the groundwater mounding analysis requirements and calculations necessary for the use of infiltration BMPs. This material is covered in depth in Chapter 13 of the BMP Manual. My goal with this presentation is to cover the requirements under the stormwater management rules, as well as concepts, methods of calculation, and examples on relation to groundwater mounding analysis. The rules require we assess the hydraulic impact of the proposed development on the groundwater table and design the site to avoid adverse impacts. Well, in order to describe what is an adverse impact, let's take a look at what happens when we infiltrate stormwater. Below the surface, the groundwater table rises locally, and then it needs some time to spread out before returning to stasis. When we force a concentrated amount of water into one area, we get mounding. This increase slows down the ability of the basin to infiltrate, so we can have problems if this increase is large enough to slow down the rate of infiltration beyond our 72-hour window, or from repeating the slowing down over and over, the basin can experience failure. Additionally, as this mounding spreads out, it can reach adjacent structures such as basements and septic systems. Let's look at a nice graphic that illustrates this. This illustration is in the paper prepared by Glenn Carlton from the United States Geological Society, or USGS. We have a house near an infiltration basin. The blue color area below everything is known as the saturated zone, whose top surface is the seasonal high water table. Imagine, if you will, that it rained. The rain has now stopped and runoff has collected in the basin. As stormwater infiltrates below the bottom of the basin, we get a temporary localized increase, or mounding, below the basin that is caused by stormwater infiltrating into the subsoils after the storm event. In order to dissipate, the volume of water under the curve has to move outward and downward until it returns to how it was before the rain. We need to calculate the maximum height of the mounding in order to assess the impact of infiltrating stormwater on the basin and on nearby structures. One method of calculating the height of groundwater mounding is covered in Chapter 13. That method, known as the Hantush equation, dates back to 1967. It requires the computing capabilities, such as that found in the Excel spreadsheet developed by the USGS. You basically enter in certain parameters and then click the Calculate button to see the result plotted. Additionally, the user gets results in the cells of a spreadsheet. Now, there are certain ground rules pun intended, for using the spreadsheet. So we'll go over what parameters we need to define, and then we'll look at making sense of the plot the spreadsheet creates by virtue of a macro. This is a screenshot of the hand-touch spreadsheet. If you have used the spreadsheet in the past, you may find this spreadsheet a little bit different from the spreadsheet that was posted on the USGS website. That's because in March 2020, DEP published and adopted a new BMP manual chapter titled Chapter 13, Groundwater Table Hydraulic Impact Assessments for Infiltration BMPs, which provides both detailed guidance regarding the input values and examples illustrating how to conduct the groundwater mounding analysis. With permission from the USGS, we modified the spreadsheet. Here's how it looks today. All of the calculation algorithms are the same, but the units and the notes on the use of the inputs are modified to be consistent with other chapters of the BMP manual. Chapter 13 and the spreadsheet are available at the link shown on this slide. To get more familiar with the hand-touch spreadsheet, let's define the parameters listed here and establish the assumptions for their use in the spreadsheet. The first input parameter is the recharge rate. In the spreadsheet, you must use the design value for the vertical saturated soil hydraulic conductivity, which is 1/2 of the tested value of the vertical saturated soil hydraulic conductivity from soil testing performed in accordance with Chapter 12 of the BMP manual. The second input is the horizontal hydraulic conductivity, which is rarely tested on the scale of a single site just for the purpose of conducting a groundwater mounding analysis. Therefore, you will need to use presumptive values based on the site's location. If the site is located in the coastal plain, then the horizontal saturated soil hydraulic conductivity is presumed to be 5 times the recharge rate. That is the vertical saturated soil hydraulic conductivity. If the site is located outside the coastal plain, the horizontal saturated soil hydraulic conductivity is presumed to be the same as the recharge rate. If you recall, Lisa provided us in Module 2 with the link to the Bureau of GIS website where you can determine if your site is in the coastal plain. That link is also found on this slide. The next parameter is the specific yield, which is the volume of water that will drain from a soil specimen due to gravity divided by the total volume of the soil specimen. Coarse soil will likely have a higher specific yield than fine-grained soil having the same porosity. Specific yield governs how much water the unsaturated zone can store when recharge reaches the water table. The more water that can be stored in the unsaturated zone, the lower the resulting mounding. Therefore, a soil having a higher specific yield may result in a lower mounding height than a soil having a lower specific yield when other inputs remain the same. For groundwater mounding purposes, specific yield is not calculated by subtracting field capacity from porosity. The hand-touch spreadsheet assumes that the BMP is rectangular in shape, and the sides of the BMP are vertical. So we use the width and length of the bottom area of the BMP, also called the footprint. But since the mounding is highest at the center of the BMP, for graphing purposes, we use 1/2 of each dimension as the inputs for the length and width, which correspond to the X and Y axes, respectively, as the inputs. Now for BMPs that are not rectangular in shape, we have some additional guidance here. So for circular shaped BMPs, use the radius of the circular basin as both X and Y. For irregular shaped BMPs, convert the shape to a rectangular shape that has the same depth of stormwater runoff to be infiltrated and is best fitted to the original shape. And then if a BMP is designed with sloped sides, use the bottom footprint as the length and width of the BMP and use the total volume of the runoff to be infiltrated divided by the area of the bottom footprint to calculate the duration of infiltration period. And we'll define duration of infiltration period in just a couple slides, so bear with me. For the initial thickness of the saturated zone, unless it is proven by a field test showing the thickness of the saturated zone beneath the proposed BMP, the default value is 10 feet. Note that the thickness of the saturated zone used in the hand-touch spreadsheet is not the thickness of a large regional aquifer. It is the distance from the seasonal high water table to the first hydraulically restrictive layer. If a value greater than 10 feet is used, it must be accompanied by on-site testing results that demonstrates the value used is appropriate. The input value must never exceed 75 feet, which is based on the preliminary results of research conducted by the USGS. The exact maximum allowed value may be subject to revision based on the final results of the research. Any on-site boring used to justify a value greater than 10 feet must be a continuous sampling boring for the entire drilled depth. The duration of infiltration period, T, is equal to the time required for the BMP to drain the volume of stormwater runoff at the specified recharge rate, and is equal to the volume of runoff to be infiltrated divided by the product of the infiltration area and the recharge rate, where the volume of runoff to be infiltrated may be either the runoff volume produced by the water quality design storm or the volume of runoff to be discharged through exfiltration, if exfiltration of runoff during basin routing is used. The maximum duration of infiltration period that may be used in the hand-touch spreadsheet is 72 hours. When hydraulically restrictive soil layers are present below a proposed infiltration BMP, one solution may be soil replacement. Let's analyze how that may impact the input parameters. In the situation where the soil is replaced all the way down to the seasonal high water table, there are a couple of things to note. The recharge rate shall be 1/2 of the tested the tested vertical hydraulic conductivity of the soil replacement media, up to a maximum of 10 inches per hour. However, the horizontal hydraulic conductivity shall be calculated based on the original soil, since the original soil will be surrounding the BMP outside of the soil replacement. The low permeability soil will still be present in the surrounding area, and the resulting horizontal hydraulic conductivity will still limit the ability of the runoff to be dissipated into the saturated zone and may result in high groundwater mounding in the unsaturated zone. Therefore, the use of soil replacement and basin designs must still be carefully evaluated with a groundwater mounding analysis. Example 7 in Chapter 13 of the BMP Manual describes a groundwater mounding analysis scenario where soil is replaced down to the seasonal high water table below an infiltration BMP. And it's important to note, if a shallower soil is to be replaced, rather than replacing the soil down to the seasonal high water table, the recharge rate shall be 1/2 of the lowest vertical saturated hydraulic conductivity of the remaining native soil. Continuing on, there are some important relationships between maximum mounding height and the input parameters to note. Delta H max is the maximum height of the mounding, and the value calculated by the hand-touch spreadsheet is that which occurs at the end of the duration of the infiltration period. This is explained on page 17 of Chapter 13. However, the hand-touch spreadsheet does not further calculate the mounding as it spreads out over time. We'll talk about this further in just a moment. A lower mounding height will happen when horizontal hydraulic conductivity increases, specific yield increases, or the initial thickness of the saturated zone increases. You cannot just use the results from the spreadsheet as it appears. The results have to be checked against the physical constraints of the design. If you get a resulting mounding height that is higher than the distance between the basin bottom and the seasonal high water table, you do not get an artesian condition. It means the recharge rate is adversely impacted by a reduced hydraulic gradient and will be slower. That means you'll have to run the spreadsheet again after you make some changes. Because there is a proportionality between the recharge rate and the duration of infiltration, as shown in this equation, the changes include using a smaller recharge rate and a correspondingly longer duration of infiltration for the same infiltration area and the same volume of runoff to be infiltrated. Furthermore, if the mounding height just touches the bottom of the BMP, the rate of recharge will also be slower than the design value for the vertical saturated soil hydraulic conductivity. When this happens, you can stretch the duration of infiltration period while decreasing the recharge rate, or you can spread the volume of runoff to be infiltrated over a larger area. When opting to increase the footprint, you'll be able to use a shallower depth. There are some limitations associated with how the hand-touch spreadsheet operates. The graph produced by the spreadsheet is comparable to a snapshot in time of the mounding that occurs at the end of the duration of infiltration period. Since it's a snapshot, it does not depict what happens over time, as the mounding height decays and spreads out. During decay, while the maximum mounding height under the center of the basin will reduce, the mounding will expand into the horizontal direction and potentially cause the tails of the mounding curve to rise higher than the height at the beginning of the decay. This means that if an underground structure appears to be above the mounding predicted by the spreadsheet, or out of range of the mounding altogether, it may still be inundated when the mounding height decays, since the hand-touch spreadsheet does not provide the height of the tails of the mounding during the decay period. Therefore, caution should be used when applying the spreadsheet to analyze adverse impacts to subsurface structures in proximity to an infiltration BMP. Now that we better understand the inputs to the hand-touch spreadsheet and the results it provides, let's go to some examples that illustrate the method and what to do with the results. The examples presented today are two of the ones included in Chapter 13 and are arranged from simplest to more complex. After a straightforward example, we'll look at an analysis that shows infiltration will be at a slower rate than the design saturated soil hydraulic conductivity and what changes need to be made because we encounter an impact. In other words, we're going to see two different scenarios. For the first example, a major development located in the coastal plain proposes an infiltration basin, whose bottom footprint measures 50 feet by 50 feet, to infiltrate 5,000 cubic feet of runoff generated by the water quality design storm. The maximum depth of ponding water is designed to be 2 feet. Soil testing was performed in accordance with Chapter 12. The soil testing report shows that the seasonal high water table is 7.5 feet below the 6-inch thick bottom sand layer of the basin. The tested soil permeability rate of the most restrictive soil horizon below the basin is 4 inches per hour, and no nearby underground structures are present. Let's start with some basic calculations. Typically, the soil testing provides results in inches per hour, so the value for T would also use hours as the unit of measure. For the duration of infiltration period, we divide the volume of runoff to be infiltrated by the product of the infiltration area and the recharge rate. Also, remember that the recharge rate is 1/2 of the slowest tested saturated soil hydraulic conductivity rate from soil testing. Therefore, the duration of infiltration period is calculated to be 12 hours. When using the hand touch spreadsheet, it is helpful to make a table of inputs and the results, so they are ready to be added in later to the report. These inputs are organized to follow the order they appear in the hand touch spreadsheet. The recharge rate is the first parameter entered into the hand touch spreadsheet, but it needs to be converted to feet per day if you are using the older version. Feet per day is just inches per hour times 2, so here we would use 4 feet per day for R. The specific yield is set equal to the default value of 0.15. The horizontal hydraulic conductivity is equal to 5 times the recharge rate, since the infiltration basin is located in the coastal plain. The basin measures 50 feet by 50 feet, so we would just input half of each of those dimensions, since the analysis is performed at the center of the basin. And the duration of infiltration period is obtained from step 1. We also needed to divide hours by 24 to get the number of days, which is 0.5 for this example, if we're using the older spreadsheet. T is less than the upper limit of 3 days. The initial thickness of the saturated zone uses the default value of 10 feet. Alternatively, you can grab screenshots from the input section of the hand touch spreadsheet, shown here with the parameter values from the previous slide entered in the gold shaded cells. This version of the spreadsheet is one that allows time to be input in hours rather than days, and recharge is in inches per hour. With the inputs entered, I clicked the dark blue Recalculate Now button and took this screenshot after the macro finished plotting the blue curve. The results show in the red cell in row 16 the maximum height of groundwater mounding, represented by the variable delta H max equals 6.07 feet, which I have circled in light blue. And this is what will occur at the end of the duration of infiltration period. To put this into proper context, I've also superimposed a symbol representing 1/2 of the bottom of the basin. Since the seasonal high water table, which the spreadsheet always sets at y equals 0, is 7.5 feet below the bottom of the sand layer, the temporarily elevated groundwater table, located at y equals 6.07 feet at the center of the basin, where x equals 0, will not reach the bottom of the sand layer. Therefore, the assessment shows no adverse hydraulic impact to the proposed infiltration BMP from the groundwater mounding. Remember that had the height of the mounding been high enough to intersect the bottom of the basin, it would mean the mounding will interfere with the infiltration capability of the basin. We would have to run a new model or trial that would involve increasing the basin footprint to spread out the volume of stormwater being infiltrated. That would result in a lower depth of stormwater runoff in the basin, since the volume is the same, and the duration of infiltration period would have to be recalculated before the spreadsheet is run again with these new parameter values. If you recall the duration of infiltration period equation from slide 21, the footprint area is in the denominator. So we would see the duration of infiltration period decrease proportionally as the area increases. Next, let's talk about when things go wrong, meaning adverse impacts. This slide is not for the example I just presented. It is meant to show you what happens in the spreadsheet when the groundwater mounding height is too high. If you click on the dark blue Recalculate Now button and the results show delta H max in the area I have circled is larger than the distance from the seasonal high water table to the bottom of your BMP, you won't be able to tell just by looking at the graph. In this case, the seasonal high water table is 8 feet below the bottom of a basin that is 90 feet in length. The height of the mounding is calculated to be 9.51 feet. The plot by itself looks normal, but is it? We have to understand what is being plotted and check it against the reality of our design. The depth to the seasonal high water table is 8 feet. This does not mean groundwater will rise up in real life above the bottom of the basin like this. It means the temporary elevation in the groundwater table, located at the center line and above the seasonal high water table, will intersect and exceed the elevation of the bottom of the sand layer, meaning it interferes with the infiltration capability, and therefore it will take the BMP longer to drain. Adjustment of the basin design is therefore needed to reduce the impact of groundwater mounding. So we have to adjust our parameters and run the spreadsheet calculation again. To do that, we have to reduce the value for R. We don't know exactly how much it will slow, but my first attempt would try reducing it by 50%. However, we are not ready to click Recalculate. The horizontal hydraulic conductivity is not adjusted since it is not affected by the reduced hydraulic gradient in the vertical direction. However, the duration of infiltration period must be proportionally adjusted to reflect the slowing down. For example, we would double the initial value for T if we halved R. Although we don't know the exact rate to which the rate will slow, even if it is slowed by 1/2, we're going to check the mounding for a value of T that is within the maximum allowable time period. Sometimes we call this stretching the infiltration period. Next, we recalculate and check the result to see if delta H max is now less than the distance between the seasonal high water table and the bottom of the BMP. You might try this one more time with T a bit longer, as long as the R value is proportionally reduced. If that doesn't work, you're going to check Chapter 13 for an example of changing the dimensions of the infiltration area. With that explained, let's move on to our second example. We're going to look at a dry well for the example of an adverse impact. Even a small BMP can cause one. A site is located outside the coastal plain. A 7-foot high by 5-foot diameter dry well is proposed to store and infiltrate 137.4 cubic feet of roof runoff from a single-family home for the water quality design storm. The house has a basement floor located just above the groundwater table. The edge of the dry well is 10 feet away from the house. Soil testing was performed in accordance with Chapter 12. The soil testing report shows that the seasonal high water table is 2 feet below the bottom of the dry well. The tested soil permeability rate of the most restrictive soil horizon below the basin is 4 inches per hour. And the dry well is circular, so we calculate its area to be 19.6 square feet and input it into the equation to calculate the duration of infiltration to be 42 hours. Using the same type of chart, here are the values for our input parameters. 1/2 of the slowest tested saturated soil hydraulic conductivity rate is used for the recharge rate in the spreadsheet. The specific yield is the default value of 0.15. The horizontal hydraulic conductivity is the same as the recharge rate since the site is located outside the coastal plain. The duration of infiltration period is 42 hours. And the initial thickness of the saturated zone uses the default value of 10 feet. The results show the maximum height of groundwater mounding, 1.11 feet, that will occur at the end of the duration of infiltration period at the center of the dry well. The temporary groundwater mounding does not encroach upon the bottom of the dry well, where it would have impaired infiltration had the mounding extended that high. Are we done? No. The rules require we also check the impact to the adjacent structure. Recall that the vertical axis is situated at the center line of the dry well, and the groundwater mounding curve is symmetrical on both sides of the dry well. The basement is 10 feet away from the edge of the dry well, which is 12.5 feet to the left of the center of the dry well. The spreadsheet results indicate the water table is also temporarily raised approximately 0.4 feet at the basement wall location nearest the dry well, which is an adverse impact prohibited by the rules. Therefore, the dry well may need to be moved farther from the building to avoid the adverse impact caused by the proposed infiltration. Per the USGS paper, an increase of 0.25 feet or less is an acceptable depth for underground structures to be temporarily affected by groundwater mounding. The mounding height at 20 feet from the dry well is just less than that. But considering the limitations of the hand-touch spreadsheet I brought up earlier, it would be advised to place the dry well even farther than 20 feet from the basement, since the mounding decay, which is not modeled, may result in a rising of the groundwater level at the basement area higher than as it is shown in the hand-touch spreadsheet. This example shows that even a small infiltration BMP may have an adverse impact on nearby underground structures. So if you haven't read it, Chapter 13 includes a lot more examples. Please see Example 7 in the chapter for guidance when replacing soil below an infiltration BMP. Also see Example 8 for the situation where exfiltration is used in the routing calculations, and a mounding analysis is done for the volume exfiltrated for the 100-year storm. Additionally, Chapter 5 includes examples with groundwater mounding analyses and includes exfiltration in the routings, which is allowed in certain circumstances for the green infrastructure BMPs. All right, thanks everyone for your attention. Here's my contact info, and I'll check in with our moderator, Chang-Yi, if we want to address any questions.
I think I answered all the questions in the chat. So let's continue the quiz. Thank you.
All right. So up next will be Manesh with the third quiz. Please stand by while Manesh takes control.
All right, thank you, Peter. So it is time for quiz 3. I think you all know how this works now, so I'll be moving through these first few slides fairly quickly. As I'm sure you remember, using a new tab or window, you have the option to follow the link shown at the top of the slide, which will take you to the training website where you can find the quiz links at the bottom. You will also find the link for quiz 3 at the bottom of this slide here, which staff will also be pasting into the chat right now. Or you may use the camera app on a smartphone to scan the QR code found in the bottom right of this slide. This QR code will also be posted in the chat by our staff. Once you click on the link for quiz 3, you will be directed to the quiz, which should now be open on SurveyMonkey. Do remember to make sure to click submit at the end of the quiz to get credit for completing it. You must answer every question before you can advance to the next screen and finally submit. And also, you may only take the quiz once. So here's everything all in one place. Just a reminder, the quiz link is also in the body of the email that was sent for the invite to this module. It is now 3:48, so please do come back in 10 minutes and we will get ready for our quiz review. All right, welcome back, everyone. Let's get started with the review. So we will go right to question 4. Which one of the following is not a green infrastructure BMP? And the answer here is D, extended detention basin. Question 5, when reviewing water quantity calculations, which of the following must the reviewer check for accuracy? And the answer here is actually D, all of the above: land covers, basin design, and hydrographs. Question 6, which of the following conditions must be met when a stormwater BMP is allowed to infiltrate the entire runoff from the 2, 10, or 100-year storms? And the answer here is D, all of the above. Question 7, what is required as part of the municipal stormwater management plan to grant variances or exemptions from the design and performance standards? And the answer here is C, mitigation plan. Question 8, if you have an impervious surface that has existed for 10 years, but have removed this impervious surface prior to the submission of the application that includes a stormwater management review component, can you still use this impervious surface as an existing condition in the stormwater management calculations? And the answer here is B, no. Question 9, true or false? If a project has been reviewed by the NJDEP Division of Watershed Protection and Restoration, formerly known as dealer or land use, the municipality does not have to review it for compliance with its Stormwater Control Ordinance or RSIS. And the answer here is B, false. Question 10, which of the following would be exempt from the groundwater recharge standard? And the answer here is B, previously developed portions of a site in a designated center. Question 11, true or false? Reducing impervious surface on a redevelopment project always meets the water quantity control standard. And the answer here is B, false. Question 12, can an infiltration basin be designed with a perforated underdrain pipe as a means of discharging runoff from the basin? And the answer here is B, no. Question 13, true or false? The TSS removal rate requirement must be met on each subdrainage area of a site unless the discharge from each drainage area converges to a single discharge point on site. And the answer here is A, true. Question 14, when can a wet pond be considered to be a green infrastructure BMP? And the answer here is actually C, both statements above must be met. Question 15, true or false? When the groundwater mounding reaches the bottom of a BMP designed to infiltrate, the infiltration into the subsoil would be adversely impacted. And the answer here is A, true. Question 16, what method is used to calculate the groundwater mounding height? And the answer here is B, the hand tush spreadsheet. So I know that was a quick little quiz review, but due to time constraints, we had to speed that up. But that is the end of our quiz 3 review. Module 4, our final module, is this coming Thursday, September 18th at 1 p.m. Invites to Module 4 will be sent out tomorrow. As always, thanks for your attendance and participation. Before we do end the module, Changi and Lisa, are there any last-minute questions or concerns that need to be addressed?
I don't have. I think it's end of the training, so everyone you can leave. And if you have questions, you are welcome to email to our DWQ account. Thank you very much.